Hello everyone, I'm Piyawat. Today I would like to present our paper, Can Capacitive Touch Images Enhance Mobile Keyboard Decoding? This is work done by myself together with Chanqing, Billy, Cedric, and Shumin from Google. Let's start from the motivation of this work. As we all know, tap typing is one of the most used text entry methods for mobile touchscreens. However, unlike physical keyboards, mobile touchscreen keyboards are relatively smaller and do not have physical boundaries between keys. This could make the keyboard interpret the user taps differently from what the user intended to type. And this usually happens if the user lands their finger near the key boundaries, not the key centers. We use the term key decoding to refer to the process of the keyboard determining the key that the user intended to type. And in the literature, most existing work relies mainly on the touch centroid position X and Y to decode the user tab. In other words, if we look at the right-hand side figure, most existing work use only the red dot X and Y position as a spatial signal for predicting the key that the user intends to type. However, in fact, we have richer information that we can use for decoding, which is the capacitive touch sensing image or the raw sensor values on the right-hand side. If you can see that here, the red dot was actually derived from this sensor image. We may call it the touch heat map because it shows where the user taps on the screen. However, this information was discarded during key decoding. In fact, we have seen from literature that the heat map has been proven useful in several UI applications. This includes predicting hand postures, predicting finger orientation, touch gestures, touch pressures, and so on. Therefore, in this work, we ask a fundamental question which hasn't been answered before. Can we use the touch heat map to enhance tap decoding accuracy beyond using just only the touch centroids? And we conducted experiments to answer this question in this paper. Let's start from the decoder where we implement to utilize the touch heat map. So we choose logistic regression-based spatial models for its efficiency and simplicity. And we implement this model to predict and integrate key from the touch features. Here we focus on 28 candidate keys, including A to Z, space, and period. And the spatial model outputs the predicted probability of each candidate key. In terms of the feature sets, to compare between the centroid and the heat map, of course, we try using only the centroid, using only the heat map, and using both centroid and heat map, so that the differences in performance can be attributed to the inclusion or exclusion of the heat map. For the centroid, we have X, Y, and we compare it with the center of each candidate key. As a result, we have 56 features. For the heat map, we use a Pixel 6 Pro device, which has 39 times 18 heat map cells. But because we work on keyboard decoding, we can focus only on the bottom 16 rows of this heat map image. Therefore, we have 16 times 18, which is 288 features in total, and we can use a combination of these two. Furthermore, we devised a novel representation of the heat map called heat map overlap vector, which is more lightweight. As you can see, the heat map overlap vector results in only 28 features, which equals the number of candidate keys. I will explain next how to construct this, and we can also use the heat map overlap vector together with the centroid. After we have the features, we normalize it to stay in the range of -1 to 1 before we input it to the logistic regression model. For this heat map overlap vector, it is a novel representation, as I mentioned earlier. It has 28 features, which corresponds to the 28 candidate keys we focus on. To construct this vector, we start by initializing all the value as 0, and then we look at each non-zero heat map cells in the heat map image and try to distribute its value to the keys that overlap with the active cell. For example, if we look at the brightest cell on the right-hand side, assume that it has an intensity value of 100, and 70% of the area of this cell overlap with the key W, while the other 30% overlap with the key Q. So we distribute 100 here, 70 to W, 70 to W and 30 to Q. And we do the same for all the active cells in the heat map image. Then we will get the heat map overlap vector. Apart from the spatial models, which are like those logistic regressions, we also apply some additional techniques to ensure smooth user experience. The first thing is skipping unambiguous cases. If we know that the centroid lands close to a key center, we are sure that this tab is not ambiguous, and we can answer that key directly. Neighbor key filtering is the technique where we focus only on the keys that are surrounding the touch centroid or under the touch centroid, so that we can reduce the space of candidate keys to only the key that have high chance to be the intended key. And the last technique is to use the output from our spatial models together with the language model scores. Here we combine the scores of those by multiplication and answer the candidate key with the maximum combined score. Now, let us move on to the experiment. To do this experiment, we need to first collect the data, which is a data set of pairs of touch data and the key that the user intended to type. Therefore, we set up copy typing task where we recruit 24 participants and ask them to use two-time typing to type the prompt shown on the screen. And after we obtain the data, we try to align each touch point with the key in the prompt so that we can have a pair of touch point and the intended key for training and evaluating the model. This is the results of an offline experiment where we test the trained model on a new set of data collected from a different set of participants, different set of prompts, and we've seen that after including the heat map into the feature sets, we can reduce the character error rates. And moreover, if we compare the heat map, the flattened heat map and the heat map overlap vector, the heat map overlap vector perform better in reducing the character error rates. And this trend still holds even after we apply the 3 additional techniques that I mentioned earlier. So this shows the potential of the heat map for decoding intended keys. We confirm these results by conducting an online interactive evaluation by actually deploy the centroid-only model and the heat map overlap vector models on the Gboard, and with the 3 additional techniques to ensure the smooth typing experience. We conducted a user study of 16 participants, asking them to copy type prompts. Some of the prompts are English phrases which do not appear in the when we collect the training data, and the others are random strings of 8 characters each. And we asked the participants to perform 4 typing tasks, and 2 of them used the centroid model and the other 2 used the heat map model. However, the participants didn't know which models they were using. We asked their satisfaction after each block, and we found that the users were more satisfied in the keyboard performance when the heat map model was in use. The scores of the centroid model was around 3.625 out of 5, while the heat map got 4 out of 5, and the results here, the difference here was statistically significant. This is also reflected by the typing metrics, including the word per minute, which reflects the typing speed, and word error rate, which reflects the typing accuracy. And the heat maps was shown to improve the speed of the typing and the accuracy of typing of the participants, especially for English phrases. But for random strings, we found that the results were not significant. And to investigate this, we look at the accuracy of the touch centroids, and we found that the user type a lot slower when they type random strings because they need to pay attention to the sequence of letters that they are not familiar with. Therefore, most of the touch points are accurate themselves. But if we look at only the ambiguous keys where the models were applied, we see more significant results between the heat map and the centroid model, and the heat map is better. So in conclusion, both objective and subjective results show that the touch heat map can improve the decoding accuracy over using just only the touch centroid. And the heat map overlap vector that we devised is a good representation that is lightweight and more generalizable than the raw flattened heat map. Some open questions here. Because when we type, we may hold the finger on the screen a bit longer, and it may generate a sequence of heat maps, not just one single heat map image. In this work, we use only the first frame of the heat map. But actually, the question is, can we leverage more than that? Can we use like other frames beyond the first frame, or can we even use the heat maps from the previous touch points to help decoding? This is still an open question. And also generalization to other device models, other keyboard layouts, other typing postures remains to be studied in the future. That's all for the presentation, and we release our dataset at this link, or you may scan the QR code here. Thank you for your attention.
Thank you for the great talk, Sohail Kianzad from Huawei. So one question that I have is that do you still need to multiply the heat map by the Gaussian model, or do you have you used that also? Like, what is the full pipeline? Are you also multiplying that by the language model?
So we use the spatial model, which is the logistic regression model, together with the language model scores. We combine these two. But maybe this is not like the optimal way to do it. There may be like a better way to combine the two signals together or use additional signal. But we don't want to complicate these things, because the goal of this paper is to check or to confirm how useful the heat map is. But in practice or in production, we may have additional signals together.
Hi. So the result is, it is known to be meaningful features for predicting intended keys to use the heat map of the capacitive. Why not use it, and what do you expect as the hurdle? Like in practice, I expect the engineers might need to consider the burdens of adding additional model on it to calculate it, and because it's not requiring any modification of the device, or you can just change the API and just improve it. So if it's like known to be meaningful, like I want to know what's the future of the production level impact of this result.
Okay, I think there are two points here. Of course, we need the modifications of the model, like the decoder inside, because this is like a small part that works together with others, and we need to train this model, especially for like different device models. That is the part that we need to do to make it work like universally or as much as possible. But in terms of latency or like workload, overhead of this, we in the online interactive evaluation, we also measure the latency of compare these two models, and we found that okay, the Centroid use around like 0.8 milliseconds to decode, while the heat map use around 1.1 milliseconds, but all are not perceivable by the users.
So I can expect in a few years for the update?
In development.
Okay, thank you.
Hey there, Dustin Freeman. It's really nice to see a rigorous version of this. I had to do something very sketchy for a much larger interface recently, so thank you for the documentation. I'm quite curious, the threshold to define the center of the key at 0.25 of the width of the key, did you consider that, tuning that at all, like per key? I'm just curious if that number was good enough and you went with it, or, yeah, I'm just surprised that it worked right away and you didn't need to do a search for it.
Yeah, we didn't like tune this number. This is just based on our intuition, but we found it worked well, and therefore we use this number. But in practice, of course, there may be a better number if we can tune it. Yeah.
Okay, thanks.
Thank you. Thank you all.